So this is all totally obvious and trivial. So now let me make this a little bit fancier. By formalizing this calculation and recasting it in a form which we'll find very useful when we apply it to not just topological dynamics, but the real dynamics that we care about. So what now we'll derive is the totally central result. If you understand this, you understand almost everything. And it has a fancy name. It's called topological. Is not important. That's a special example of it. It's called trace formula. And we'll see this notion of trace formula several more times. So there's some trace formula in dynamical systems. That one nobody ever told you about, so it'll be just a trace formula. You won't care about it. But if you do quantum mechanics, which you won't do this, semi-classical quantum mechanics of chaotic dynamical systems, systems which are classically chaotic, is described by Gutzwiller trace formula. And by the time you get to that one, you'll have to scratch your head a little bit. And then you'll realize there are very deep connections to trace formulas in mathematics, and especially something called Selberg trace formula, which will be something that counts eigenstates of a drum on genus 2 hypersurface, blah, blah, blah. But something that is generalization of Riemann hypothesis, and in 2 dimension can be proven, but for Riemann hypothesis we are still in deep water. This trace will get pretty fancy pretty soon, and the reason is the following. Right now we're counting the number of partitions. So we have coarsely partitioned world, and everything is described by finite matrices, and we have just learned that we can understand asymptotic property of the system, which is just counting. In topological dynamics, isn't there much to do else, because the trajectory has a value 1 or 0. So what can you do is but count all admissible trajectories, but that's extremely useful information already. And so it's just matrices, and trace will be trace or matrix, no big deal. But when you go to dynamical systems, fancier version of it we look at fluid dynamics and not just something that's in 3 dimensions, or quantum mechanics, or quantum field theory. These traces will be traces of operators, which means their matrices are work not on finite countable vector spaces, but on function spaces. So things will get pretty soon pretty grim. So ask yourself, how do you compute an eigenvalue? One way is if you look at t to the n, and you're interested in large n behavior, one thing that you notice, that if I take a trace of t to the n, that by definition is sum of all the eigenvalues raised to power n. And that doesn't matter whether matrix is diagonalizable or not. If it's not diagonalizable, then it's upper triangularizable, and the trace will only pick up the eigenvalues. So for any finite matrix, this is obvious, and it's also obvious for the powers of the matrix. So one possible way you could try to compute individual eigenvalues, if you cared about them, is to look at what this trace looks. This is maybe easy to compute. It'll turn out for us, we'll have explicit formulas how to compute these traces for different n's, and then try to extract eigenvalues by fiddling with the n's and getting different stuff. But any sensible person would instead look at determinant of 1 minus zt. Now, somebody admit somebody's formula. This is for finite matrices, the determinant is polynomial, and this is a finite product which has a 0 every time I hit the eigenvalue of this thing, inverse eigenvalue of this. Another way is to find the zeros is to look at all the zeros of this product. And it'll turn out that these 2 things are very useful to us. Of course, there are many other ways of computing eigenvalues, which may be much more efficient for a particular problem. But these are totally sensible things. And while this seems natural, when this becomes a very large matrix, and especially limit when it becomes infinite matrix. When it's talking about operators, it might be hard to make sense of it. It turns out easier to make sense of traces. So topological traces formula are natural if you're interested in eigenvalues of some matrix. And we'll be interested not only at the leading eigenvalue, but more. So for example, if you do semi-classical quantum mechanics, these eigenvalues actually be spectrum of, let's say, helium, and we'll care about first 100 or 1,000, not just one. But often one will do. A useful object to define, which I actually defined previously, but I didn't look at it very carefully, is to define a little trace. So let's define a little trace, and the idea will be this. There are certain walks, finite time walks, on the world that we use to construct our transition matrix in terms of graphs. When I maybe go from region A to region B to region C to region D, A again, and I'll define, associate with this graph, a little trace called A, B, C, which will simply be a product of transition from C going to B, then from B. So this is just matrix element of my transitional matrix. B going to, let's say, from C, I went to A. From A, I go to B. And from B, I go to C again. Now, this particular path is called walk on a graph. And if all the three elements are 1, this is an admissible walk. So, that particular walk gets value 1, I'm allowed to go. If any one of them is forbidden, this link is 0, I'm not allowed to have the walk, so this matrix is 0. But if you go to this generalization that I mentioned before of thinking of the links not just as being 0 or 1, but having a positive real value between 0 and 1, which you can interpret as probability and think of Markov graphs, then this is actually a number giving you probability that you do this walk. And now what I can do is I can decide to give every link a little value z to the n, so z to the cube, for example. And this exponent will count the length of the walk. So if I have 3 links, there will be z to the 3. And I'll get some rule that says, if this is just counting, that TABC, this walk, either has value z to the cube, and this is the same z that shows up here, or 0. I'll do that because when I look at matrices, let's just look at the binary example. I will find that trace of T times Z is Z times the first element, which is 0, 0, the second element, which is 1, 1. But I know what these things are. It means I start at 0 and I come back. So these are walks of length 1. Now when you look at Z square trace of T square, you can write it out as T11, T22, T12, T21. And as I multiply, let me just take care of diagonal terms because the trace will only care about diagonal terms. So I'll get T11 squared from here, and then I'll get plus T1221. And then there's some stuff here. And that'll be T squared 22 plus, and then I'll get, to get something down here, I have to multiply these two guys as well. And I have a T21, T12. Now notice this definition is cyclic. So this is something that only cares about ordering in which you visit the nodes, not which one is first or last. So I find out that the trace of the square is z squared times t1 1 squared plus, and I'll use this notation now, t1 2, meaning I have two terms in this product as I go down, these two terms, and I have two of those, plus t22 square. Now you can play this game for a while, and I'll just write, for example, all walks of length 4, and these are all recurrent walks. Trace means I start someplace, I end at the same point. So all recurrent walks of length 4, t4, will be, I don't go any place, so it's t1, 1, 4 times, I just hang around. t2, well, this is called 1, sorry. t2, I just stay in the same neighborhood 4 times. But then you'll find 2 times of going from 1 to 0 and then 1 to 0 again. There'll be 2 of those. But then there will be plus 4 times 1, 0, 0, 0, plus 4 times 1, 1, 0, 0, plus 4 times. Stay in one neighborhood and then go once around. So, I recommend doing this. This is a very simple exercise, and you realize that the trace to the nth power has a very simple expression in terms of the walk on the graphs. So Zn trace Tn. So these are all walks, all recurrent walks. All recurrent walks, boom, can be written as a sum of all divisors of n. So for example, 1 is a divisor of n and 2 is divisor of 4 times the number of points in a walk. So this 4, we went through 4 cycle points to do this. And then the length of the cycle, if I repeat it twice, is to the second power. So it's n divided by the divisor. Or you can write this as sum of all prime sequences. So they're distinct itineraries. For each prime you get the length of the sequence, and then you get this little trace repeated r times, but the length of the prime orbit, for example, 2 cycle has to be a divisor of the whole cycle. In other words, r times the length of the orbit that's repeating itself times n is a delta function. These are only contributions for all repeats, and we can be generous and we can say r to infinity. So now we have a very elegant formula. You might not believe me, but please do the algebra, it's totally straightforward, that says that the trace number of recurrent trajectories can be expressed in terms of all primitive recurrent or prime recurrent, the shortest recurrence of trajectory, weighted by the number of points in the primitive cycle. But there's an awkward constraint, there's a delta function here, Kronecker delta, that says they only contributes if the prime cycle, so this is sum of all prime cycles, all repeats, it only contributes if prime cycle is a divisor of a long cycle, so longer cycle is a repeat of a shorter one. Whenever we have this kind of awkward constraints, we get rid of them by some transformation. So usually it's called Laplace transformation. So if there was a Dirac delta here, we would, try to integrate over it. And so this is awkward. See, delta n getting only contribution NPR, and you're summing over these 2 integer sequences. That's a little bit of a pain. So now what we do is we take a sum of Cn and n. So this is the number of recurrent trajectories. And remember, all we're trying is to compute these eigenvalues, which will be computed in terms of traces. So we're not wedded to 1, 2, 3 steps in time. All of them are fine. But that is a sum n equals 1 to infinity, sum over the prime cycles, sum over the repeats, number of points in the prime cycles here, sum of their repeats, t to the repeat of the prime cycle, and n prime r. And now if you do the sum, you always get rid of this Kronecker delta, and we get an extremely simple formula that sum n equals 1, this is trace Zn, trace of n, is, because this now becomes geometric sum in repeats, r equals 1, but they start with 1. So we pick up 1 repeat and then 1 minus zt. Now, we know that these guys on the left-hand side are sums of eigenvalues. That's what trace to the tn is. So we can just replace this by the sum of the eigenvalues. But then we have something that Zn lambda sum off to infinity, so we know how to sum left-hand side. So on the left-hand side we get Z, because we start with 1, lambda alpha, sum over all the eigenvalues, divided by 1 minus Z lambda alpha, is, on the right-hand side, we know what the trace is, npTp. 1 minus Tp, summing over these r's. And voila! We started herding cats only today or in the last lecture. And here we are. We have a formula that says if I sum up all irreducible, all prime periodic orbits of my dynamical systems, which tell me all my possible recurrences from how I start the region come back in all possible ways. Each one of them has a weight, which in this simple case is either 1 or 0, where it's allowed. And this gives me the sum over all eigenvalues. Now, eigenvalues of this are global behavior, because remember, we started with cats, all possible cats, and let them run. That's the left-hand side. On the right-hand side, we're computing periodic orbits, which means we start at a point and go and come exactly at that point. But this is a finite dimensional state space, so it doesn't look so terrible. And here is our topological trace formula.